A new neural network architecture just dropped. Kolmogorov-Arnold Networks, or CANs, are supposed to be a rival to MLPs, something we haven't really seen, rivaling the backbone of all AI. That's kind of hard to do, but they show a method that is they slightly change how the MLP is formulated, and they use, instead of using the universal approximation theorem, they use something called the Kolmogorov-Arnold representation theorem. And the two are very similar, but the latter can be more expressive. So basically the idea is, with a normal neural network, you have your model. Your model has some inputs, and those inputs are some vector. So you have like x, I'll draw it out over here. So you have some inputs, some vector, you have like x1, x2, x3, so on, xn. So you have some vector of inputs. And this is sent through basically some MLP, some matrix multiplication, which has multiple nodes. And this will give you some, or just having one node here, is based off a linear combination of all of the inputs, and each of these are multiplied by one weight scalar, W1. So Z1 is equal to, say, W1 x1 plus W2 x2 plus W3 x3 plus so on, plus Wn xn. So this is just a linear combination of I is equal to 0 to n, W I xi. This is just a linear combination of the inputs using these weights here, and the weights are learnable. So this is the NLP, or the MLP we all know and love, and you just add more functions here, Z3, Z4, and so on, however many you want. So this is just MLP. And then you throw this through some activation. Maybe this is SILU, maybe this is ReLU, whatever you want to use. So then you get like A1 is equal to the activation, or A1 is equal to Z1 sent through the activation function, where this is maybe like SILU or something like that. Now, this is how normal neural networks are defined, but they basically say that it's kind of, so like sure it works, but it feels a bit weird that we're like, oh, we have some linear layer, and then we slap on an activation function, and then we have another linear layer, and then we slap on an activation function, and then we have another linear layer and slap on an activation function. So it feels a bit weird. Instead, what they do is they build in the activation functions into the weights. So instead of it being A1 is equal to the activation of the inputs, so x1, z1, just do c, z1. So the activation of the inputs, where each of these is a weight multiplication, or is multiplied by a weight. So just in the one node case, it would be the sum, I is equal to 0 to n, of wi xi. So this is normally how it's defined. They kind of swap it. And what we're going to do is place the activations on the weights. So their A1 is going to be slightly different. It'll be the sum, I is equal to 0 to n, of xi wi. So, similar to this, we'll get to the actual definition later, but the idea is this will now be a sum of activations, and these are going to be not just learned, they're not going to be learned weights, they're going to be a learned activation. So instead of our matrix here, so this is like a d by d matrix that we multiply by, where each part of the d by d matrix is, say, one weight, w whatever. This is just your normal weight matrix here. This will now be a matrix of activations. So this would be like A1, 1, A2, 1, and so on. And you multiply this by x usually, and you multiply this by x. So matrix multiplication by x. So instead of our weight matrix being a weight matrix, it's going to be an activations matrix that we're multiplying by. And the idea is we want to learn these activation functions instead of just telling the model which one to use. So that's the idea. So to do that, they use something called splines, and splines are, so I'm only going to get into splines a little bit. I'm certainly not an expert in splines, nor am I close to one. I'm going to put a video in the description if you really want to go into how splines work. It was a video I watched. It was very good, but high level overview just to see how they're kind of using splines. So splines come from these things called Bezier curves, which is a way of creating a curve out of these points. So the idea is you can have, say, some points. We'll use 4 points here. So P0, P1, P2, and P3. And this here defines a curve, something like this. And this curve is defined basically as, so it's defined like C of t is equal to the sum I is equal to 0 to n, where n in this case is going to be equal to 3, of bi n of t, pi, where this is our point. So this is our ith point. So this point, whatever that may be. And this is going to be the weight at that point. So polynomial weight at that point. And t is defined between 0 and 1. So t is in 0, 1. So at time 0, you basically have, so you're basically following the curve that you're defining here along time. So at time is equal to 0, you have a point here on the curve. At time is equal to 0.5, you'll have a point here. At a time equal 1, at time is equal to 1, you'll have a point here on the curve. So this is basically defining, this is your function here, and t is where you are on the curve. So the sum here is our function that we're defining, and the function is a sum of the basis and the points here. And to see where you are on this function, you just look at where you are on, you just give the function a value of t, and t defines where you are on this curve. So defines the curve, and you can see where you are on that curve using t. Now, this is good. this is good and all, but what we want to do is extend this to much larger values of t. So we can do this with something called B-splines, and B-splines basically stitch these together. So you have multiple Bezier curves, and that allows you to approximate functions a lot nicer in a continuous way. So this one I defined with 4 points. Imagine I define one with, say, 3 points. This would be, I think this would be order 3. Order equal to 3. I think so. I think it's based off that one. But now imagine I have, say, I want to approximate a better function, or like one with more curvature. So I can do that. I'm just going to draw out the diagram I have on the left here. And this will be P0, P1, P2, P3, P4, and P5. So if we have an order 3 polynomial, or an order 3 B-spline, you can essentially approximate this using every set of 3 points here. So, and you can do that by chunking this up. So you can define the first curve, say right here. And what this curve is going to be defined on the interval t0 to ti, or t1. So this right here is just our first Bezier curve like we did up here. Now we can add on another Bezier curve, and that will basically extend the function that you're defining, say right here. And this function is going to be defined in terms of a different set of points, say, I guess it would be these 3 or these 4. So you would define it using those points there, and so it wouldn't use this point here. Yeah, this one would be P0 to P3, using these 3 points, no, using these 4 points here. So that's what this first curve is defined by, and this one's using P1 to P4. So it's using these 4 points here. So it's just extending it slightly. And you can extend it again, extend our function again by adding another Bezier curve going, say, like right here. And this curve is defined by P2 to P5. So P2 to P5. So this one would be defined from T0 to T1. This one would be defined from T1 to T2. And this curve right here will be defined from T2 to T3. This first curve is defined by the first 4 points. The second curve is defined by the second 4, or by the 4 points offset by 1, and the third one is defined by 4 points offset by 2. So P2 to P5. So this is the idea. You can basically define functions on some arbitrary time interval by using multiple Bezier curves, and this is what a B-spline is. So a B-spline is defined by this function here, so S of t. So this is similar to this function here, just it's going to be a sum of Bezier curves, or basically a sum of our Bezier curves. I is equal to 0 to n, and it'll be n I k of t pi. So this is similar, except we have a different basis function. Like the basis is going to be different. So this is defined mostly by this part here. This first part, this index I, is basically the resolution. That's what I'm going to call it, the resolution. It's basically how many points you have. And for every point, you're going to have this function, and the more functions you have, the better it'll approximate the function you're trying to approximate. And then these are just the points here. So I is just the number of points, or I is the index for every point here. So in this case, n will be equal to 5. So we'll have from 0 to 5, or n will be equal to 6. Yeah, 5. It'll be 5. This one here, k, is the order. So in this case, the order was 3 because we used 4 points. So it's just like the order up here. This was order 3. It's the number of points minus 1. In this case, it was order 3 as well. But if and that just defines how your curves are defined. We could use an order 5 or an order 4 function, and that would just have 2 Bezier curves, one defined by P0 to P4, and the other defined by P1 to P5. So the order defines how you're making your curves, how you're making your Bezier curves. So this function here is a mess. I don't know if anyone has any intuition behind this mess here, but it's basically a recurrence relation, and the function gets more complicated as you increase the order. But the idea is here. I'll just draw it out over here. In this case, we would have 5. This would be n is equal to 5. So let me draw it out over here. So basically, you can kind of visualize this by having your function and your time axis. This would be n I k of t, and this would be your time axis. So we have 6 points here, so I would have to draw 6 curves. I'm only going to do a few. So let's say this is 1, 2, 3, 4, 5, 6. So t is equal to 1, 5, and 6. So the first curve would be something like that. The second curve will be offset by 1. The next curve will be offset by another 1. And the next one will be offset by another 1, and so on. So this would represent P0. This would be the function going with P0, and this would be N0. In this case, k is equal to 3, because we have a order 3 Bezier curve. We're dealing with order 3 Bezier curves, so this would be N3 of t, and this corresponds to P0, and that's this one here. And this would be N13 of t, corresponding to P1. This one would be I is equal to 2. So that first index, this one would be I is equal to 3, and so on. So you would have I is equal to 4, and I is equal to 5. So you'd have 2 more. I guess I could draw them out. So you'd have 1 more there. So 7 and 8. Yes. So you define these curves here, and these are only defined whenever we have the three intersecting curves. So it's not defined until you get to around, say, here-ish, and here-ish, like around right there. And you can imagine, so this is just like the weight of the point at the time. And you can imagine kind of taking a walk along this here. So if we have, so as you walk along the curve along time, you can imagine walking along here. So if we start here, we have a lot of point 1. So if this curve right here represents point 1, and the weight of point 1, you have a lot of weight for point 1. You have a little bit of weight of point 2 and a little bit of weight of point 0 and point 2. So this curve represents point 2, the weight of point 2. This curve represents point 1, and this curve represents point 0, and this curve represents point 1. So at time step like 2 is 2.3. This represents the combination of 0.01 and 2. So that would represent something like here-ish, something like that. And you can see here that this point doesn't care about point 3, 4, and 5. And you can imagine as you increase time by walking along the curve here, you go from left to right. So if we say step all the way over here at time step 5, we have a lot of point 3. So maybe this is like right there. We have a lot of point 3. We have a little bit of point 1 and 4, or 2 and 4. So you can imagine as you walk along this curve, you're changing how much of each point you have, and you do that by this here. And this is just the representation of the function n. So this is basically weighing each point according to this mess here and according to this function here. But just imagine as you walk along the curve, you're changing how much of each point you have, and you can do that in a very continuous way by creating something like this. And they show that up here, that this activation can be composed of these functions here, your basis functions, and you can imagine walking along this curve here gives you your function, and the function is defined by a weighing of these here. So this is the idea of B-splines. You basically want to define a function by having basically a bunch of simple functions that you can combine together, and it'll give you this complicated function. And I guess that's the main idea with neural networks. You have a bunch of simple functions, combine them together to make a complicated function. But this here is going to approximate our activation function. This is going to be a learned activation function. So yeah, this is going to define the activation function, which I'll show you down here. So the activation function that we're defining, it is up here, is defined like so. So if we have some input, so that would be this. So if we are looking at, yeah, so this is going to be our activation here. So if we have an input X, so an input X, one of these, we send it through a basis activation, and this basis activation is just SILU. This is just, I'm guessing, so it has like a good start to where, a good starting point, because the spline is 0 initialized. So basically you start off with a activation and then a weight. instead of a wait and an activation. So it's kind of flipped around, but I'm guessing this is so you can start out with some activation, kind of guiding the model and giving it some gradient to work with, or giving it gradient flow to work with, instead of having everything initialized to 0. So this is just a basis, I guess some bias that you're putting in saying, oh, maybe this activation should start off as a silu, and you can work from there. The more important part is the spline. So the spline is going to define our activation, or our activation function that we're learning. So this is a static activation function, and we're adding a learn activation function. And like I said, this is weird because usually you apply a wait and then an activation function. Here we're applying an activation function and then a wait. So this is just your normal learned scalar wait. So the spline we're defining is similar to what we defined earlier. It's similar to this function, except instead of this being a point, this is a trainable parameter. So instead of us doing an interpolation of points, we're essentially defining a combination of splines. So it's slightly different. Instead of the splines defining the combination of points, we're having a model learn a combination of splines. Another point to make is that instead of us giving the model, or instead of us giving the splines a time step, so a time step on this curve, we're parameterizing it by the input, because time there isn't really a representation of time in our neural network. So the input is x. The input is not time. The input is x, and that means that that basically means that our model is defined on some domain based off the number of time steps we give it. So if we go back to the example over here, this case we had 5 points, and the points here are going to be the weights, and the weights are going to be learned. And this, instead of this being like the number of points we have, you can think of this as the resolution of the model, or the resolution of or the domain of the model, or the domain of the activation. So if we go back to this diagram over here, if we have a resolution, or what I'm calling the resolution, to be 5, so n is equal to 5, then your model is going to be defined in a range between t is equal to 0 and t is equal to 5, unless you extend it. So the model is only going to be defined between these points here. And along these points here, the model will be able to weigh each of the splines that we have here. So these are splines, and the model will be able to weigh each one. And the weights, or the weights it learns for every spline, is just going to be a learned parameter. So you can think of this as a combination of splines, and this will create a function. So if we go up here, this is our activation here, and this is learned. So we have our domain here between t0 and t5. So this has an order of, 7? Or 7, or no, not an order of 7, but rather a order of 3 and like a resolution of 7, a g of 5, so 5 plus 2, so g of 5. And so it's defined in this domain, and you can weigh these splines here in such a way that it defines a continuous function between the x value here and the x value here. And it'll define this continuous function here depending on how you weigh each spline within this domain here. So this defines one activation, and this is just going to be the activation function that you send your values through. So if we go back to the neural network up here, this combination of 7 splines that we have here is going to define, I drew it, yeah, it's going to define rather not a weight, but an activation. So I'll draw it out over, I'll just look at this one. So it's going to define the activation that you send through. So every point here is going to be a combination of the activation. So if we have 2 inputs, this function here will be a combination of 2 inputs. And usually you would just have weight 1, weight 2. Weight 1 is multiplied by x1, and weight 2 is multiplied by x2. But in this case, we're going to have this be a sum of the activations of the learned activation functions. So it'll be a sum of this value here, where this may be a function of, say, 5 splines, and this one here, where this activation is going to be a different set of splines. And you can see that here they have kind of this function-looking thing right here, showing that the spline, or showing that the activations are different because the splines are weighed differently. So this is the idea for a KAN. You're just instead you turn your weight matrix into an activation matrix. You'll then sum those activations. So see, we just sum them. The output is just the sum of the activations, and the activations come from these functions that you're learning, which are composed of splines. So your function here, or your activation, which you're summing for every node, is going to be a sum of a basis activation, your learned spline activation sent through a weight, or multiplied by some weight, and that's what you're doing. So learning activations using these splines. Now, one nice property you get from learning these splines is you can actually increase the resolution of the splines, and they also show that up here. You can increase the resolution of the splines, and you can extend your function. So if you want your model to have a higher resolution, so still I'm calling G like the resolution, you can add more splines. So you can take the function that you currently have, and say you have a G of 5, a resolution of 5, you can increase it by adding more splines and increase it to, say, 10. And this allows, you can basically have the exact same function, but have them basically give the model more parameters to learn if you want to do continual learning. And they show in a later example that the model doesn't have catastrophic forgetting if you just increase the resolution, allowing the model to learn over time, while multi-layer perceptrons do have this catastrophic forgetting. So that's one nice property you get from this. They have a bunch of examples and some interesting things they get from this parameterization, but this is the main method. It's just you have instead of having your nodes where your output node is a linear combination of your input nodes sent through an activation, you instead have your output node is going to be a linear combination of the activated inputs. So sent through an activation, multiplied by a weight, sum it up. So I've made this model sound really good, but there are a lot of things that are weird about it that may make it not as good as we may like see. So they did a good job marketing this paper, but so there are problems such as the limited domain problem I said. So I'm curious if this limited domain is going to run into problems because it's not defined outside the domain, the spline. So you can't, I'm wondering if that'll lead to any issues. Perhaps it won't. Perhaps you can just squish it down into the domain you have. Another problem with that is, since this is learnable, this could be an unstable function. Nothing is telling the model to be stable. It learns what it wants. So this may lead to instability issues at scale. Talking about scale, they don't scale their model very, very much. They use like a few layers and a few hundred, maybe 1,000 nodes, but they don't scale this very much. And they also don't test this on like real problems. They only test it on like toy problems, from what I've seen. Like they don't test it on MNIST, which is quite strange. Another problem is this thing has more parameters. So if we look here, and as you would expect, it has more parameters. Like a normal MLP has n squared L parameters. So n is the width. What is L? L is the depth. In this case, it is n squared L G plus K, because these are from the learnable activation. So it has more parameters. That may be bad, though they say it's more expressive. So you may be able to get like the same number of parameters in the end using less nodes because it's more expressive. We'll see if that's actually the case with scale. Another thing that is problematic is all the way down here. 32. Where's 32? Right here. So as you would expect, like a matrix multiplication is super easy to make. Cans are 10 times slower than MLPs given the same number of parameters. We should be honest that we did not try hard to optimize the can's efficiency, though we do deem can's slow training more as an engineering problem to be improved in the future than a fundamental limitation. So, like if you look at the way this is formulated, the weight matrix has to be calculated every time. Like you can't just do a multiplication and be done with it. You have to recalculate all the activations, or perhaps like you have to recalculate all the activations and then you can do and then you add it all up. So it's a very heavy process, while an MLP is very, very light, easy. It's just a matrix multiplication. The matrix here is not easy to calculate. It's not very quick. So these are a few of the problems that are going to be run into with this method. So it's not perfect in any way, but it seems like it shows promise. I'm wondering if this thing can scale with some research being put into it. But at the moment, it probably doesn't just scale. You probably can't throw this at a transformer and it'll work. You probably can't create canformer with this formulation alone. So there may have to be research that goes into more activations, though I could also be wrong, and this thing could be amazing at transformers, though it doesn't seem like it could be because they only tested on toy problems at small scale. So let's go through some of the results. So I mentioned extending the resolution, and they mentioned that here, like they start with a resolution of 3, so just 3 parts of the spline, and they increase that, and they show that you can do like this continual learning, and it'll learn a better representation, learning off the last set. Though it looks like there was like a loss jump here after it added a few, but in general, it looks like it utilizes the splines pretty well, though it does decay to a point. If you add too many, then there becomes a problem. But notice that this is only on a really small network with, 2 layers here. So we don't know if that scales. They claim that the model is interpretable, and this is probably one of the coolest parts about the paper. You can basically reconstruct physical processes with this. I do not know if this is a physical process or not. Probably, but they say they have a method here which allows you to basically get a physical process out of this, which is pretty cool. And if this generally can give you a physical process, you have a model that learns something, and you can extract a nice functional representation out of that. So even if this doesn't scale, it's still quite cool that you can throw this at a smaller like differential equation, and perhaps it can give you some solution to it, that like this one here. Maybe, I don't know if that's true, but perhaps it can. I don't know how much this method generalizes, where they basically take the trained model on some problem and they reconstruct the solution for a physical process. So maybe this generalizes, maybe it does not. It would be cool if it did generalize in this case. So they also claim that the model is accurate, though the problem is this is just on toy data. So like this method here, our method learns this function better than an MLP, but it's also like it's like not a super complicated function. So it can learn these weird functions, not weird functions, but it can learn like exponential and sine a lot better than MLPs can, because of the way it's constructed with the splines. MLPs cannot learn those very easily. So they show that like it has a limit where like MLPs just can't learn that function because it just can't learn that function, while their method can at smaller scale, though, like I said, they don't bring this to a larger scale. They don't bring it to a large number of parameters. They only bring it to 100 or like 1,000 parameters. So they don't scale it a lot. And this is the test RMSE. And they don't put it on large problems like this. They only put it on these toy problems here. So maybe this does scale, maybe it doesn't. I'm leaning towards probably not until you add more to it. You'll probably run into instability issues. Another cool thing about this is it avoids catastrophic forgetting, like I mentioned earlier. And this is the problem I was talking about. They have this continual learning. I think this is on a PDE task or something like that. But they basically have multiple phases, and they give it different sets of data, and they show that cans basically remember the old data, while an MLP would just totally forgets the old data, and it doesn't worry about that at all. So yeah, this generalizes. This would be quite cool because continual learning is a problem right now with like MLP, with current models. If you train it on new data, it's just going to forget the old data unless you have some incentive to make it not forget the old data. So if this is the case, this is quite cool. That it can do continual learning, and it doesn't have this forgetting problem as bad as MLPs. Yeah, and then they have a bunch of other things that they mention, but they're all on like smaller problems. So if you're curious, go ahead and read through the rest of the paper, but they're all small problems, and it does really well at these small problems, but I don't know if this will scale. I don't think it'll scale. It's not going to be this new thing that we all think it is, but it's still a cool architecture, and it's a cool idea, and I wonder if we can actually get this thing to scale. Throwing some more research at it, but cool method. Let's see where this goes in the next couple of weeks.